So I hope you tried on the in-class activities to make good progress on proving the division algorithm, far enough that when we do the proof here, the proof will make sense. All right, so all this video is dedicated to is just giving you a formal proof of the division algorithm for polynomials based on the ideas in the in-class activities. So our theorem is if f is a field and if f of x or g of x are polynomials with coefficients in that field, where also f of x is a non-zero polynomial, then there exist unique polynomials q of x, r of x, our quotient and our remainder, such that g of x equals q of x, f of x plus r of x, and either r of x is the zero polynomial or the degree of r of x is less than the degree of f of x. Remember, if r of x is the zero polynomial, it doesn't have a degree, so we can't say what its degree is less than or greater than equal to. All right, so as in the integer form of the division algorithm, we have an existence part and we have a uniqueness part. We're going to start with the existence part, so we're going to first prove that a quotient and remainder exist as stated in the theorem, where the remainder has degree less than f of x. All right, so we're going to first define our s. That's going to help give us our sort of minimum polynomial. And that is going to be the set of all polynomials s of x, such that s of x is equal to g of x minus q of x times f of x for some polynomial q of x. Now, this is just the set of all possible remainders without regard to the degree. So one of the things that we're going to be looking at is the degree of the polynomials and finding the polynomial with the lowest degree. And since zero polynomial does not have a degree, we want to get rid of the case where zero is actually in that set. But that's not going to be so bad. In the case that zero is in S, and by zero I mean the zero polynomial, we have 0 equals g of x minus q of x times f of x for some polynomial q of x. If we solve for g of x, we get g of x equals q of x times f of x, and then we can just let r of x be the zero polynomial, and then we get g of x equals q of x, f of x plus r of x. Okay, so that completes the theorem, in at least the existence part of the theorem in that particular case. And now that we've eliminated that case, we can assume that all the polynomials in S are non-zero. And in particular, that means every polynomial in S has a degree of 0 or more. And not only that, but the degree of the polynomial is a whole number. And that means we can use the well-ordering principle not on the polynomials themselves, but to the degrees of all the polynomials. So if we look at all the possible degrees of the polynomials, it has to be a least element in there, which means that there has to be at least one polynomial, r of x, whose degree is minimum among all the polynomials in S. So it has the least degree among all the other polynomials in S, among all the other remainders. So we have r of x equals g of x minus q of x, f of x for some polynomial q of x. And so that means that g of x equals q of x times f of x plus r of x. So again, we get ourselves a quotient, we got ourselves a remainder. The only thing that we have to prove is that the degree of our remainder is less than the degree of f of x. All right, so we're going to do this directly by contradiction. We're going to first assume that the degree of r of x is greater than or equal to the degree of f of x, and then we're going to prove ourselves a contradiction. So we're going to want to write out in polynomial form r of x and f of x. And I'm writing it in descending powers of x, because we are going to be focused on those leading coefficients, that am and bn. And I should mention, those really are the leading coefficients, the way we're writing them. We know that the degree of f is less than or equal to the degree of r, and the degree of f is going to be n, and the degree of r is going to be m, and that just tells us that n is less than or equal to m. And we're going to write those polynomials so that we don't have any coefficients past our leading coefficients. So we're assuming that am and bn are both the zero element, or both not the zero element in our field. So what we're going to do, and this may look strange if you're looking at this video without having done the in-class activities, but if you looked at the class activities at least far enough to figure these things out, what we're going to do is we're going to multiply our f of x by this very strange polynomial am bn inverse times x to the m minus n and see what we get. So I should first note that Bn inverse exists. Bn is a non-zero element in the field, and F is a field, so every non-zero element has a multiplicative inverse. And the other thing I want to note is that x to the m minus n makes sense as well. Since n is less than or equal to m, that x to the m minus n is going to have a non-negative exponent. If somehow n were bigger than m, x would have a negative exponent. That would cause us problems because that's not a polynomial. Polynomials all have non-negative powers of x. All right, so just a reminder of what r of x and f of x are. And let's see what happens when we multiply f of x by am bn inverse times x to the m minus n. Well, some interesting things happen. The first term, when we multiply that by the first term, the am times bn inverse multiplied by b, the b and the bn and the bn inverse are both going to cancel out each other, and that's just going to leave us with the coefficient am. And then also that highest power of x, that x to the n, when we multiply that by x to the m minus n, we add the exponents, and that gives us x to the m. So that means when we actually multiply those out, we get am x to the m, just as we engineered things. And then the rest of the terms are just multiplied by, well, first of all, we multiply the powers of x by x to the m minus n. And so we end up with the powers x to the m minus 1, x to the m minus 2, all the way down to x to the m minus n for the lowest one. And then also the coefficients are going to be multiplied by am bn inverse. Okay. But not on the first one, not on the leading one, because our bn and bn inverse cancel each other out, leaving us with am. So notice that r of x and am bn inverse x to the m minus n f of x both had the same leading term. And we did that on purpose because when we want to subtract those, and when we subtract those are going to cancel. Those leading terms are going to cancel. Which means that if we let r prime of x be r of x minus that polynomial, am bn inverse times x to the m minus n times f of x, r prime of x is going to be a polynomial whose degree is less than degree of r of x because those leading terms canceled out, leaving us with lower powers of x than we had before, lower powers than r has. So if we then solve for r of x in that equation, we get r of x equals am bn inverse times x to the m minus n times f of x plus r of x. And now we're going to put this all together in our formula for g of x. Remember g of x? That's a very important part of this theorem. Remember we had g of x equals q of x, f of x plus r of x. But now we can replace r of x with the expression that we had for r of x. If you forgot what that is am bn inverse times x to the m minus n times f of x plus r prime of x. Notice that those first two terms have a common factor of f of x. We're going to factor that out. So we got that polynomial, that q of x plus all that other stuff, times f of x plus r of x. And now we've written g of x in another quotient remainder pair. So we have quotient q of x plus am bn inverse times x to the m minus n, and a remainder of r prime of x. And note that that r prime of x has a degree that's less than r of x. But then that contradicts the fact that r of x was the remainder with the smallest degree, and that means that we couldn't have had such a remainder. So that takes care of the existence part of our theorem. We have that means that r of x has degree less than the degree of f of x. All right, so now we're going to take care of the uniqueness part of the theorem, and it's going to go very similarly as it did with the integers, with maybe some slight twists. So we're going to, let's suppose we have a quotient remainder pair, g of x equals q of x, f of x plus r of x, where r of x is either 0 or its degree is less than f of x. And then we're going to show that q of x and r of x are the only quotient and remainders that satisfy the conditions. So we're going to do this directly by contradiction. So that means we're going to pretend we have another quotient remainder pair, q prime of x, r prime of x, where degree of r prime of x is less than the degree of f of x. And we're going to assume, since this is contradiction, that either q of x is not equal to q prime of x, or r of x is not equal to r prime of x, or both. And then we're just going to prove a contradiction. Once we get to a contradiction, we're going to be all done. So remember, we have g of x equals q of x, f of x plus r of x. We also have g of x equals q prime of x, f of x plus r prime of x. And if this looks familiar, a lot of what we do is going to be exactly the same as we did for the uniqueness in the division algorithm for integers. We're going to move all the quotient terms onto the left, all the remainder stuff on the right. Then we're going to factor out the f of x. And then we're going to look at the degree of the polynomials on each side of the equation. So we're going to look at the left-hand side of the equation and look at what its degree is, and the right-hand side of the equation, look what its degree is. All right, let's see what we get. The left side is going to be the trickiest, so let's go ahead and dig into that one first. So remember from homework, we actually proved something about this, that if f is a field and thus an integral domain, when we have two polynomials a of x and b of x that have degrees, right? So neither of them is the zero polynomial. Then when we find the degree of a of x times b of x, we get the degree of a of x plus the degree of b of x. So when we multiply polynomials together and find their degree, it's the same as taking the individual degrees of the polynomials we multiplied and adding them together. So if q of x minus q prime of x is not equal to 0, which we definitely want to consider as a possibility, then, well, we have degree of f of x times q of x minus q prime of x equal to, well, there's two polynomials multiplied, so we add their degrees. We get degree of f of x plus the degree of q of x minus q prime of x. Now, I don't know, and neither do you, exactly what the degree of q of x minus q prime of x is, but it is certainly at least 0, right? So this whole thing is going to be greater than or equal to the degree of f of x. All right, so since f of x times q of x minus q prime of x is equal to r prime minus r prime of x, that means that degree of r prime of x minus r of x is also greater than or equal to the degree of f of x. They're the same polynomials, so they have to have the same degree. But this is problematic because each of r of x and r prime of x is either 0 or it has a degree less than the degree of f of x. And that means it is impossible for the degree of r prime of x minus r of x to have a degree that is the degree of f of x or more. So that's a contradiction. And remember, that contradiction led or followed from the assumption that q of x minus q prime of x was not 0. And so since we got that contradiction, that means q of x minus q prime of x is 0. And that means that q of x equals q prime of x. But now we're in great shape to figure out what's the relationship between r prime of x and r of x, because when we subtract those two, we get f of x times the quantity q of x minus q prime of x. Since q of x minus q prime of x, since q of x is equal to q prime of x, that means we get f of x times 0, which is the 0 polynomial. And that means that r prime of x equals r of x. And that contradicts our assumption that one or the other are not equal. And that completes our proof. So that takes us to the end of the proof. There are no in-class activities to go along with this one, so you can just go on to the next topic.